Welcome to Honors Strict Pre-Calculus, Vectors in a Plane. There's certainly some things worth pausing perhaps here and going over, but a lot of them become self-evident as we move through some example problems. And as said in a great movie once, a vector is just a magnitude and a direction, which is often a magnitude, often a force represented by a distance. So let's jump right down to number 12 here and take a look. One thing to note is that magnitude and direction does not include a location. So vectors, which are oftentimes and generally written with lowercase bold print, as for example the U and the V, they can be the same and not be in the same location. They just have to be represented with the same length and going in the same direction. So how we find the form of a vector, this is listed up above. I'm not going to make all of these bold all the time, but once I probably ought to do it right, is we get the x component, and this vector is going, it doesn't show up real well here, but this vector is going this way, which means I'm going to use a golf analogy along the way. We hit our golf shot from here to here. That's our entire golf shot. But when we do this in components, we want to find out how much the x has changed. The x's went from 0 to -3. To find out the change of those, and this is listed in the notes above, we take where the x's ended at, -3, minus where they started at, 0. And where the y's ended at, -4, minus where they started at, 4, which means vector u in component form is -3, -8. The ball moved 3 to the left and 8 down. So there's vector u. Here's vector v. I'll make it bold just one time. Vector v, the x components, it's going this way as well. Doesn't show up again very well, but there it is. The exponents went from 3 to 0. So we ended at 0, 0 minus 3. Y's ended at -5, started at 3. So v is -3, -8. So they most definitely have the same direction, left 3, down 8, left 3, down 8. And if we understand those are just two sides of a right triangle, Pythagorean theorem gives us the hypotenuse, -3, 8, -3, 8. If those are legs of right triangles, they obviously have the same hypotenuse value as well. So u and v are the same vector. Okay, in exercise 13 through 24, find the component form and the magnitude. And the magnitude, which is the length of this. Our vector's going this way. We'll call it vector v as they ask us to. So vector v terminates here. We wind up at 3 for an x component, minus we start at -1. We wind up at 5 for a y component, minus we started at -1. So vector v is 4, 6. And for the magnitude, we could go ahead and draw this. We could use distance formula. We could use Pythagorean theorem, which are both exactly the same thing, or we've already got our lengths here of 4 and 6. So our magnitude, which is denoted this way, is square root of 4 squared plus 6 squared. Just the back end of Pythagorean theorem. Give us that hypotenuse. So we get 16 plus 36 square root 52, which is square root of 4 times 13, which is 2 square root of 13 for magnitude v. You got this whole double absolute value symbol, just refers to magnitude. Whatever's in there is going to be a vector. All right, let's move on. A lot of mechanics here before we get to some challenging stuff. Find the component form and the magnitude of vector v. Same exact problem, they just give us the ordered pairs, which if they weren't fractional almost makes things easier. So we'll call it v as they ask us to. And vector v's x ended at 1, minus it started at 5/2. The y entered at 2/5, minus it started at -2. I'm going to clean that up a little bit. I could write this as 2 halves minus 5 halves and 2/5 plus 2, or 10/5. So vector v in component form is -3 halves, 12/5. Nothing to it. 25 to 30. Use the figure to sketch the graph. Now, to sketch the graph of the specified vector. And then they have a copy of it. But we're going to go ahead and just try to work this one out. And we're just going to kind of ballpark. U is a vector going in this direction from right to left and up. V goes in this direction. Accentuate those a little bit. And we want to find the result of taking vector u first and then subtracting vector v from it. And it's probably about exactly what you might expect is going on here. I'm going to take u, try to get the same direction, the same distance, or better said, the same represented magnitude. That looks about right for u. It's about like that. So my first golf shot takes me to right here, and then minus v would be v in the opposite direction, or as we talked about in polar equations, we're going to go v but throw it over our shoulder. So negative v would look like that. I want to take my second shot from here. That right angle, or that what appears to be a right angle, would be preserved, but in the opposite direction, trying to get that same distance. So here is u. This vector is actually negative v. Use the figure to sketch a graph of the specified vector. Now this is a whole new vector, u minus v. And that u minus v vector actually end up being, where did my golf ball end up? And I just had a pen break on me, so I'm going to get a different pen here. Try this. Hang on just a moment. And technical issues with the pen. Here we go. So here, this pinkish one, which still looks pretty dark here, this is u minus v. Okay? That's truthfully right here the whole answer to the problem. This is really scratch work, so maybe you would want to do that as dotted lines. Okay, so here we go. Second problem. I want to take vector v first, which looks like, I'll do this one dotted, looks about like that. My first shot takes me to right here. Then I want to add just half of u. So in the u direction, just half of it. It's only about that, about this long, probably about here. And that's where, after my second shot, my golf shot was. But the answer is this. So we had vector v, we had vector 1/2 u, but we ended up with vector v plus 1/2 u right there. Hope those colors, you can see those a little bit. I don't think I'm going to use colors too much going forward, but let's take a quick look and see if I can get a better contrast on that. Maybe a little bit better. Okay, let's move on. Here's one of the nice things about vectors, and these rules are shown on the front page of the note sheet. You could back up the video if you need to. The nice thing about adding, subtracting, and multiplying what are referred to as scalars, we'll talk about that when we get down to that one, is the rules are exactly what you would expect them to be. Problem A, we're supposed to find u, vector u, 5, 3, plus vector v, -4, 0. We're supposed to find that. And vector u plus v, all you do is, it's our golf shots. My first golf shot went 5 to the right, and my second one went 4 to the left, so I'm a total of 1 to the right. First golf shot went up 3, second one went up 0, 3 plus 0, 3. For part B, I'm supposed to take u, 5, 3 minus v, negative 4, 0. It's as easy as this. 5 minus negative 4. 5 plus 4, 9. 3 minus 0, 3. That's simple. Exactly what we would expect. C, 2 times u. I'm going to shortcut this one a little bit. 2 times u, that's 10, 6. Just double u. Hit the u shot twice for the golf analogy. 10, 6 minus, hit the v shot 3 times, negative 12, 0 is 10 for the x component. 10 minus negative 12, 10 plus 12, 22. 6 minus 0, 6. Isn't that easy? The only way they can try to be tricky here besides give us a fraction is, notice they shifted our order here. We'll be careful with that. I want 1/2 of v. Half of vector v would be half of negative 4, negative 2, half of 0, 0. I want to add to that 4 u's. U is 5, 3, so that's 20, 12. 4 of each of those. And I get 18 and 12. Negative 2 and 20, 0 and 12. Okay. Then you get to see this. Looks a little bit different. This is what's called linear form of vectors. And here's the deal that we need to know. I is the vector 1, 0. That's not a given for this problem. That is always in vector land. I is not square root of negative 1 in vector land. I is one step to the right, no steps up. And j is 0, 1. No steps to the right, one step up. I looks like 1, 0. I looks like this. J looks like that. So now, A, B, C, D, all the same. I'm just going to jump to C just to show that and save a little bit of time here. We should be in pretty good shape on the other ones. C was 2u. So this is vector u. I just becomes this. So this is vector u right here. U is 2 of these. So 2 of these, 1 zeros. We got 2 steps to the right, minus 1 step to the left. So 2 steps to the right minus 1 step to the left, negative 1. And then we're supposed to subtract. Oh, is this C? I've got 2 times that, by the way. I'm sorry, I got 2 u's. So u, I probably should write this. U is 2, negative 1. Excuse me. And V is negative 1, 1. So we need 2 U's minus 3 of the V's, which is negative 1, 1, which gives us 4, negative 2, minus 3 times negative 1, negative 3, 3 times 1, 3. Notice I didn't distribute the negative with it. I still have the minus outside here. 4 minus negative 3, 7. Negative 2 minus 3, negative 5. And the other problems are just like that. We're just using these vectors as we did in number 38. In the interest of time, I'm going to move on. Use the figures to write the vector in terms of the other 2 vectors. I'm supposed to rewrite vector v. It's like I've got to get the ball from here to here on my tee shot, or that's where the hole is, even if it takes multiple shots. But v is not an avenue on the way. There's a building in the way. I can only go along these paths, but to get there we can see I could go this way. I could go negative u, which takes me the u distance opposite direction, because use this way, so opposite direction, and then a positive plus W. And if I wanted to name W in terms of U and V, I could say to get from here to here, I have an alternate route to go U plus V. Or U, to get from here to here, I could go W and then minus V. Lots of options. 46, very similar, 2 V's. Well, 2 V's would get me down to here, and one way to illustrate it could be I could go here, here, I could do another U, because again we can move those, and then another W. So it could be backwards U, forward W, backwards U, forward W, or obviously negative 2 U's plus 2W, which would kind of look like this. Go negative U, come over a W and over another W. All right. All mechanical so far. Find a unit vector. For a unit vector, back to magnitudes. That means the hypotenuse equals 1. Unit vector. The magnitude equals 1. Verify that the resultant has a magnitude 1. If we do it right, we're going to know that it should be 1. So we've got a vector that takes us left 2 and up 2. Would look like this. But we're to the left 2. This, however, has a magnitude of Pythagorean 4 plus 4, 8, square root of 8, 2 square root of 2. We want to be in the same direction. I'm not going to scale this. I'm going to scale this one differently. We want this, however, to be 1. And I want to know what x is and what y is. The good news is that these triangles are similar. Going in the same direction, they're similar. So I can just go x is to negative 2 as 1 is to 2 square root of 2. Multiply both sides by negative 2. X is negative 2 on 2 root 2, which is negative 1 on square root of 2. X is negative square root of 2 on 2 when we rationalize. And there's a quicker way to get there. We would know this is 45, 45 if it's similar, and we could just divide square root of 2 right in the first step. But this will work if they give us points like 3, 7 for a vector. You can go similar triangles. We'll do that quite a bit. Okay, and y, well, y dot dot dot, it must equal x because we know this is a 45, 45, so y dot dot dot, y is negative, or actually positive square root of 2 on 2 since it goes up. Okay, find vector v with the given magnitude. We need magnitude of 3 in the direction of negative 12, negative 5, wants to look like that. As a triangle, this would be left 12, this would be down 5. But we want to have the same direction, and now instead of unit vector, I want that magnitude to be 3. I need x and y. I need the components of the vector. Well, here's where we need similar triangle. Good news here, Pythagorean triple. We can go Pythagorean theorem, but we're going to get a magnitude of 13 over here. So x is to negative 12. Whoops, do that again. X is to negative 12 as 3 is to 13. X is negative 36 on 13. Y is to negative 5 as 3 is to 13. Y is negative 15 on 13. So magnitude we're finding vector v, magnitude 3. The component form of vector v is negative 36 on 13, negative 15 on 13. And most definitely worth noting on this that you can factor out of here. I don't know what the back of the book answer is, but I know I can factor out of here an on 13, and I might even be tempted to factor out of here, say, a negative 3. But I'm going to factor out a 3. And I get negative 12, negative 5, and it's a really good time to play scientist and see all of these parts, 3 on 13, negative 12, negative 5, they're all in there. If we were working with this type of problem over and over and over again, this would imply there's a very good chance we could come up with a direct route. Okay, direction. Again, this is 2 steps to the right and 3 steps down. 3 steps up backwards. So 3 steps down. Same problem. So here's this vector, 2 right, 3 down, something like this, 4 and 9, 13, square root of 13. We want magnitude 10, same direction. So we want something that looks very similar, but magnitude would be 10. And there's our similar triangle game again. So x is to 2, as 10 is to square root of 13, x is 20 on square root of 13, or 20 square root of 13, on 13. Y is to negative 3, as 10 is to square root of 13. Y is negative 30 on square root of 13, or y is negative 30 square root of 13 on 13. 20 square root of 13 on 13, comma, negative 30 square root of 13 on 13. If I was to, and you don't have to, here's vector v, if I was to factor out, how about this? I factor out 10 square root of 13 on 13, I would be left with just a 2 and a negative 3. And once again, if we take some time and analyze that, we got our 10, we got our square root of 13, we got our 2, we got our negative 3. Might be worth spending some time on that. Again, if you were working in this environment a lot. I'm not really a big rules guy, I'm more of an understanding guy, but if I was working in this environment a lot, I'd have a shortcut in no time. Writing linear combinations of the vectors, the initial point and the terminal point are given. Write the vector as a linear combination, that's our i's and j's. Well, component form, we would say terminal, we ended at 2, minus we started at negative 1. Y's, we ended at 3, minus we started at negative 5. Therefore, in component form, we're 3, 8, which means they didn't tell us what to call the vector, so I'm calling it v. Vector v is 3 steps to the right plus 8 steps to the left. Excuse me, 8 steps up. My mistake. 67 to 72, find the component form v and sketch the specified vector operations geometrically. We're just going to find the component form here. So v, first off, I think it's worth doing this. U is component, 2 to the right, 1 down. V is 1 to the right, 2 up, and we want v equals 2 times vector u, 2, negative 1, minus, oh, this is w, sorry, w, minus 1, 2. And now, just as we might expect, you could distribute this 2 to these guys first, or you can go ahead and combine these first. 2 minus 1, 1, negative 1 minus 2, negative 3. hit that shot twice. Truthfully, this is an acceptable answer. Hit this same golf shot twice and we'd be at 2, -6. And there is V. And moving right along here. Good pace. Find the magnitude and the direction angle of vector V. This one's a little bit clumsy, but we're going to see a really nice conclusion here. Here's 135 degrees right here at a 45. This is -1, 1, square root of 2. So cosine of 135 degrees is x on r. -1 on square root of 2, or negative square root of 2 on 2. Sine of 135 is 1 on square root of 2, or square root of 2 on 2. So this becomes V equals 8 times the vector cosine negative square root of 2 on 2 to the right, square root of 2 on 2 up, multiplying the 8, and vector V in component form is -4 square root of 2, 4 square root of 2. Let's draw it. I'm to the left, the same distance I am up. We're at 45s right here. Here's -4 square root of 2, 4 square root of 2. Find the magnitude and direction angle of vector V. Well, the direction angle is this, and that's 90 and 45. The direction angle we'll call theta is 135 degrees. How about that? And the magnitude, 45, 45, you could Pythagorean, but we can also multiply that by square root of 2, and we get 4 square root of 2 times square root of 2, 4 times 2, 8. The magnitude of V, I don't know what I was doing there. Let's go. Magnitude of V is 8. How about that? And we realize, wow, this becomes a pretty useful way to maybe name vectors in some cases. Particularly if we know the direction angle. Direction angle magnitude, we got it. Rather than we know the x component, y component, if we knew the magnitude and the direction angle, we could start with it this way. Maybe worth taking a look at that one again. Find the component form of the vector. Here we got a direction angle, 135. Holy smokes, here it is. Take a look. I'm going to go through this work, but I'm telling you, if I'm looking at 74 and playing, and I know I still have 76 to do, but these ones relate so well I wanted to talk about this one. If I'm playing scientist here, I've got a pretty darn good idea what my result's going to be. But let's draw it. 135 degrees, 5 on 2 for the magnitude. How do I get from, in this 45, from the long side to the short side? We divide square root of 2. So that would be 5 on 2 square root of 2. If I multiply that by square root of 2 on square root of 2, I get 5 square root of 2 on 4. I don't want to multiply it though, sorry. 5 on 2, if I divide that by square root of 2, 1 on square root of 2, I get 5 on 2 square root of 2, multiply by square root of 2 on square root of 2, and I get 5 square root of 2 on 4. 5 square root of 2 on 4, that's to the left. 5 square root of 2 on 4, that's up. So our component form is 5 square root of 2 on 4 negative and 5 square root of 2 on 4. Okay, and our square root of 2, our 1 on square root of 2's are coming from these 45s, and then we've got the magnitude to work into there. So we've got that going for us. Number 76. Same problem, but now maybe a little friendlier since we're used to numbers here, but we learned some stuff about this one. Let's go ahead and draw it. Right 8, down 3, gives me, this is in form 8, -3. We're supposed to find the magnitude and the direction angle. Well, the magnitude, 64 and 9. 64 and 9, 73. This is 73's root. So our magnitude of V is square root of 73. The direction angle is negative theta. If I call that theta, we're rotating this way. So let's just figure out what theta is. I can now use inverse trig functions. I think I'm going to choose tangent and stay away from the square root of 73. Tangent inverse of y -3 on x8 is theta. Now, I really just want theta as a positive value, so I'm just going to call this the triangle that contains a side length of 3 and 8, and theta is a positive value. So what is our rotation angle? Our rotation angle, theta would actually end up being backwards -3/8. So you can see we can pull that negative out in front here because tangent's odd. Multiply by negative, we're over there. We'd be in good shape. We probably just want to deal with positives and say, hey, our rotation's backwards. Okay, vector 3, 4. Three, 4, 5. How nice. We would like a magnitude, same direction, but have the magnitude only be 3. And there's our similar triangles again. They pop up all the time. X is to 3, as 3 is to 5. X is 9/5. Y is to 4, as 3 is to 5, y is 12/5. So our vector is 9, V is 9/5, 12/5, or if you like and you might, factor out a 3 in the numerator, 5 in the denominator, and we get 3, 4, and there they are again. There's our 3, there's our on 5, there's our 3 on 4. Find the component form of the sum of u and v with direction angles given. All right, there's a little bit going on this problem. So u has a magnitude of 35 at the not so convenient angle. Here's u of 25 degrees. 25 degrees, magnitude 35, x, y. But right triangle, SOHCAHTOA. From 25, x is the adjacent on hypotenuse, cosine. Cosine of 25 degrees equals x on 35. Therefore, x is 35 cosine of 25 degrees. I don't think it's too much of a stretch now to realize that, oh, if that's the case, replace this with sine, replace this with y. Y is going to end up being 35 times sine of the 25 degrees. Those are the exact value of sine and cosine. I've been led to believe, or I've been told, the back of the book has those as decimals. I would just say if you're going to decimals, make certain that your calculator is in degrees. So, magnitude 35, this is u. Direction angle 25. Then, angle V, magnitude 50, direction 120. Well, that's a little bit nicer. Here we have a 30, 60, 90. If this is 50, this must be 25, but it's to the left in a 30, 60, 90. And this is 25 squared to 3. It's up, positive. Therefore, find the component form of the sum of these. So u plus v equals the x's, 35 cosine of 25 degrees plus negative 25, and the y's, 35 sine of 25 degrees plus 25 square root of 3. As I said, I'm certain back of the book would have that as a decimal, but this is the exact answer. All right, graph the vectors and the resultant of the vectors. Find the magnitude and the direction of the resultant. Resultant means we're going to put two vectors together, beginning to end, beginning to end. So here's golf shots. My first golf shot, I'm going to let this be my first golf shot, and the ball comes to rest here. Then I'm going to apply this golf shot to it. Kind of ballparking that one right now. This has got a little bit of trickiness to it. But what's the resultant vector? The result is the ball went here, here. So I really started here, and the ball went up to there. There's our resultant vector. And you might be saying, well, what if we hit this shot first? Well, we're here to here, and then we want to apply this to it. It would be parallel. We'd be dealing with this parallelogram. So I'm going to look at this triangle right here. Let's see if I can stick with my color theme. We knew I could. I'm going to be looking at this vector. What do we know about it? We know this side is 300. We know this side is 400 with this triangle. This angle right here is 25, and here's the really sneaky part. If I put an east-west reference line right here, take a look at this 135 degree angle right here. That's the angle between my east-west and my magnitude 300 vector. This is 135, meaning this part right up here is 45. And this angle would be equal to this angle because they're on parallel lines, alternate interior. That angle is 25. This angle is 25. Here's my triangle. Looks something like this, with a 400, with a 300, with a total of 70 degrees right there. Side angle, side, I can solve the triangle. We are looking for the magnitude. We're also looking for the total direction angle. We're going to go for magnitude first. Law of cosines. M squared, magnitude squared, equals 400 squared plus 300 squared minus 2 times 400 times 300 times cosine of 70 degrees. Or let's solve for 70 degrees. Or let's solve for, excuse me, we're solving for m squared here. So m equals big square root here. Not solving for 70 degrees. We know 70 degrees is 70 degrees. And we're going to go to calculator on that one. But that's the exact answer right there. So we'll do it this way. Second, big square root of 400 squared plus 300 squared minus 2 times 400 times 300 times cosine of 70. Everything look good? Everything looks good. And that is 409.77. So M is 409.77-ish. Just about. So we've got the magnitude. Now we need the direction angle. Well, the direction angle to this vector is this. And that angle's 25. If I refer to this angle right here as fish, then theta, our direction angle, equals 25 degrees plus that triangle angle plus fish. All right, we need to find fish. Fish, law of sines. Sine of fish on 300 equals sine of 70 degrees on M, 409.77. Therefore, fish equals, leave a blank, have to multiply 300 times sine of 70 degrees, have to divide that by 409.77, and have to get rid of sine to get fish alone. Sine inverse. Sine inverse of 300 times, I'm in degrees, sine of 70, we'd be in big trouble already if I wasn't, divided by 409.77. And we get fish is 43.47-ish plus 20, or actually theta equals fish 43.47 plus the 25 degrees. So I need to add on 25 and I've got theta. Theta is 68.47 degrees. So a lot going on that problem. Okay, kind of weird wording on here. Oh, by the way, in case I forget, problem number 100, there is a separate video for that referred to as a classic tension problem on Purple Shirted Nerd YouTube channel. So I've got this one all by itself. Find the angle between the forces given the magnitude of their resultant. Hint, write force 1 as a vector in the direction of the positive x-axis. So positive x-axis, force 1, 3,000. My first golf shot went 3,000 straight right. And then I have another force of 1,000. And force 2 is a vector at an angle of theta. Well, I don't know how big theta is, so I'm going to try to make some sense out of this. My first golf shot went 3,000. My second 1,000. If it went another 1,000 here, the total result would be 4,000. I don't think it came back this way. I don't think my next shot's back this way because that would not allow that magnitude to get bigger. I think it's somewhere out here, but I'm going to try to represent it maybe about a third as long. That's probably a little bit too long. Where this is 3,000, this is 1,000, and our resultant right through here has a magnitude of 3750. Well, we've got sine, 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 or side, side, side. This is law of sines. Now, what they're asking for, right, force 1 is a vector in the direction of, find the angle of forces given the magnitude of their resultant. We're looking for the angle between the vectors, and it is tempting to say it's this. But the angle between vectors is measured from starting points, and this guy's starting point would be right here. Same vector, same direction, same distance, or magnitude. There's that parallelogram again. So I really want to find this angle, which is not a part of my triangle, but that angle is right here. I'm going to call this one theta. That's the angle we want to find, but we can find fish. Here's that triangle. Not drawn particularly well. Where I've got a 3,000, a 1,000, a 3750, and an angle fish. Law of cosines. 3750 squared equals 3,000 squared plus 1,000 squared minus 2 times 3,000 times 1,000 times cosine of fish. Solving for fish. I'm going to leave a little blank. It was opposite 3750 squared. We have to subtract the 3,000 squared. We have to subtract the 1,000 squared. We might think we need to add, but all of this is attached to cosine with multiplication. We actually need to divide by negative 2 times 3,000 times 1,000. And now we've gotten rid of all of that, and we have to get rid of cosine. Cosine inverse of all of that. Wow. Now, I'm going to go cosine inverse of, and I'm going to use alpha y equals to write this as a fraction. If you don't do that or don't have the option to do that, you're going to need to put these in parentheses and division between those. But your numerator and denominator will both have to be in parentheses. So here we go. 3750 squared minus 3000 squared. This is the type of problem people will either drop or add an additional 0 on. Minus 1000, so we'll double check those, squared, on negative 2 times 3000, double check that, times 1000, double check that. Looks good. And we get 147 degrees. Now don't forget, that is fish. So I've got fish is 147.36 degrees, but theta, what we really want, this angle, is this angle, and that's supplementary with fish, so we really want theta equals 180 degrees minus 147.36 degrees. So let's go 180 minus our answer, 32.64. So theta is approximately, sorry about that, got off the screen a little bit, 32.64 degrees. And there we go. All right, so once again, this problem right here, this guy, there's a separate video for it. This was long enough as it is. That one's there's a lot going on that problem, but it's a very, very good classic tension problem on my Purple Shirted Nerd YouTube channel. And good luck. Let me know if I can help.